Hi everyone, we will now talk about the control of voltage and reactive power. This is our own topic in the course. This is because it becomes more and more important in the grid system to have control the voltage, as we have more, for example, intermittent power sources such as wind and solar. And you can see that how we can influence the voltage levels and also how strongly connected the reactive power and voltage are in the system. The book is additional literature that is given out in Canvas. It is the book from Voltage Stability of Electric Power Systems by Katzem and Vornas, and in the chapter 2 there. So you should have go through that chapter during this topic. We will now first start with some outline of some basic theorems that are important and how the flow of power and especially then of course reactive power are done. We know from before with the load flow analysis some understanding of how this will work, but now we'll go more in detail on the reactive power side. So let's start to look at this two-bus system. We have seen this before, but just go through how we can develop the equation for the load flow through this small diagram. So the focus is voltage control, and as you can see up here we have a transmission line with the impedance. Impedance is Z equal R plus JX. However, we typically work now with okay, we can do it like this. We are working with what we call a lossless line. So actually we only work with the reactance value of this line. So as you can see up here also, we typically have an angle here between the voltage and the current. But if you take the R away, we will have the voltage and current in phase. So for a lossless line, we have this assumption now. We have a sending end and we have a receiving end, also the voltage you can see, and we denoted the receiving end as the angle 0 up here. Also we have typically, we have learned before also, but the base power for such a system, if we work with real values, we have the square root of 3, but when we work with the per unit value, we actually just working with the product of voltage and current. Also the angle delta for you can see up here and here. I've drawn this figure now where you can see the how the voltage, how they are oscillating, the sinus here, and the angle is then the angle for the one here now be the angle difference between either lagging or leading the other voltages. So if there are no phase shifts between the voltages, that of course will be in the same manner, in the same phase here. For such a lossless line, we can actually just make a very simple equation, and this is something you probably have done before. We can write V1 times V2 on X and sine 2 delta, the angle difference, like this. And what you should also note is that the even though V1 and the amplitude of V1 is less than V2, we can say that, and still you could have power flow from 1 to 2, because we will see that is the angle, as you see also in the load flow, will demand the power flow, but we will see that the amplitude or the magnitude, I mean, with the voltage, will have really high, depending on the voltage, reactive power flow. Let's dwell a little bit more on this equation here. Actually, it's a very powerful relationship. One thing that you can remember is that often we also write this V1 here as E, descending end voltage. So we will use that a little bit later in this lecture. This reactance here is actually closely connected to what we call the electrical distance. What does that imply? Yeah, that means in this line here, if we have a large reactance, that means that the bus 1 and bus 2 is really weak connected. It has a high electrical distance between those. So if they are close, the reactance is low. So and we will see also another very important element is called the short circuit system. And we can see that it's typically written as the SC equal to the E squared divided on X, like this, reactance. So high SSC means good performance, we say. We can typically say that when we have a weak point, weak grid, or you can say connecting our grid grid system, and that means that we have actually a low short circuit ratio. So just with this simple expression, we can of course see that when we have high X, we get low E with the same voltage. So as I said before, if this increases radically in a transmission system, we have very high electric distances and we get a very weak connection between nodes or buses. And actually what we will see is that this low short circuit ratio may cause voltage instability. We will also see that the what we call the transfer limit is proportional to X reactance and to the square of the feeding voltage. So that's important. In this case, then the E here for the V1. Further thing we can look at is if you talk about this equation up here, we can say that the following: a reduction reduction of X reactance leads to smaller angle difference at the same load flow from this equation here. So a reduction of these, we can actually have a very, so this goes down, we will have a smaller angle difference between the voltages at the same load flow. Let's have a diagram to explain that. Here is the power angle curve you can see up to the left here now. This represents the relationship between the active power and the active power here and the angle separation here. So you see like 180 degrees as it can be. Then is two important things I will mention. One is that of course this is a critical point on the top, and on the left hand side here we have then the part that we have a stable region, or the region that we can work on. So this part here will be the part that is actually feasible to operate on until 90 degrees. Another thing is that here you see the reactance. So if we start to increase the reactance, means weaker grid as we know now, we will then, with the same voltage of course, if we're keeping that the same, we will see that we will have a curve that maybe comes a little bit lower with a higher, maximum P. You see here you have a higher possible P transfer. Now it's a lower possibility. From this small simple relationship we can see this here. So here I have now pointed out these two green dots here, that if you then, this other curve, if you have then a larger reactance, as you can see here, means larger reactance, we need larger angle for same power. Or opposite, a reduction of X means here leads to small delta at the same load flow. So you can see here now we have to have a higher angle difference when we get higher reactance. It becomes more separated, and you can see also we are approaching the critical point, and that is not good, because then you can get an instability in the system. Let's have a numerical value for this, but first let's see on this small feature here. Typically you can say that the flow of power is going from here, the bus 1 to bus 2, as V1 is leading the V2 with the angle difference here. In general, you can say that. But let's take the equation above here and put on some number. If we have the same voltage levels for first one and the reactance 1.7, everything in per unit, and it's time to 37.7 degrees, gives 0.2 per unit value. If we do the same now with the 1.0, and we then have a larger reactance, you need now to increase the angle to get the same power. Just with a small numerical example to see. Now let's go back to the diagram we had above here with the two bus system. So we should have like a relationship now, an equation for the total flow power in that line. So let's start with the current. An expression for that. Let's see, I V1 the angle plus 2 like this, and X of course the reactance of the line. We then have the following relationship, the Euler's formula. That means E can be expressed so the cosine theta plus J. And this leads to, we can then use that in this relationship. Then we get the I equal V1 sine minus E2 like this, and then Jx. And then we can do a trick, we multiply this with minus J imaginary value, also multiply here, because we know that minus A times here like this is equal 1, or minus 1. This then leads to cos delta plus minus J times J V1 like this, and below we then only have Ex reactance now. This can further be written like this, V1 sine delta plus K V2 minus V1 cos delta divided on X. I think this should be right. Then we have an expression for the current here, like this. And then we know that S1 equals V1 plus 1 plus 1 complex conjugated, and S2 V2 plus current complex conjugated. Or it can be written also P1 plus JQ1 S2 equal P2 plus KQ2 like this. So if we then use this expression for current into here and into here, we can have the following relationship for the total load. Start with the S2, I think. S2 equal V2 this, and then we have V2 0 degree multiply V1 OX sine delta minus J cos delta like this, and we have, yes, that should be the expression. expression, I believe. V1x sine delta, yes. V2x, V1x cos. Yeah. So we write it as S2, V1, V2, x sine the plus j V1, V2, OX cos delta minus V2 like this. This expression for PS2 can mark it also. So now we multiply the V1 and V2 in, and you can get, you see, you get V2 in square. And actually we can say that this is the P2 part, and this is the Q2 reactive power at bus node 2. If you want to calculate that. Now take for the S1, let's take it below here. Let's see, then have the S1 equals V1 cos delta sinus, sorry, let's see, plus of course V1 and J sine delta, like this, multiply with the current V1 x like this. Let's see if I have correct now. So remember that this is based on the Euler's formula. This is V1 delta. Then you multiply with the current. And this is the exponential current. Yes, minus j V2x minus V1. Yeah, that's correct. Then let's multiply it out. And we get then V1 square divided on x cos delta sine delta. So just multiply this with this. And then I get plus, now imaginary value, multiply minus V1, V2 on x cos delta plus V1 square x cos square delta, and then we get plus j V1 square x sine square of delta, and then let's see, plus V, yes, that's correct, so minus V1 squared x cos delta sine delta, and then we get plus finally V1 V2 divided on x sine delta. And here you can do some simplifications from these two. You know that cos plus sine squared is equal to 1, circle. And this goes away also with this one, yes. So we finally then get S1 equal V1 C V1 square x minus V1 like this. I think we can make it. And then the same manner we write this as the P2. Oh, sorry, P1, and this as the Q1, like this. So this was for S1, and above it was for the S2. And you see that the P1 and P2 becomes the same, but Q1 and Q2 are some different. Let's have an example to look at this. Let's see, example. And we have following line. We have reactance equals 0.2. V1 is equal 0.8. We have V2 equal 1.0. And we have P1 equal 0.7, 2 equal 0.7. So we can say that P1 equals P2 equals V1 equals V2 sine delta, like this. It's a lossless line, as you say. So the question is then, what is the angle separation over the line? Sorry, like this. That's the first question. Let's go here. Second is we want to find the delta Q over this from bus 1 to bus 2. So let's take the first one. What's the angle separation of the line? Then we can just use the equation above, and we have 0.7 equal 0.8 times 1 per unit divided on 0.2 times sine 2 delta. And this gives a delta approximately 10 degrees. So that was the first one. Let's take the let's calculate the reactive power. We calculate for Q1. So this expression V1 squared minus V1 V2 like this. This becomes 2 cos gives minus 0.7383. Take for Q2 minus V2 plus V1 to cosines delta. Yes, that's the expression, and let's fill in minus like this, and it gives minus 1.0617. And then delta Q becomes Q1 minus Q2 minus 0.783, sorry, 7 minus 617 equals 0.3224 per unit. So this system is actually vector v2 and it's a vector v1 angle separation, and the vector 1 is shorter than v2. So the active power is now flowing this way. However, you see that the voltage level is lower here, so Q are flowing opposite from this example. And the net reactive power, actually due to the line reactance, is this value here. You can see here. This is the end of the part 1 video.